Hello, my name is Shay Moran, and we will discuss today a joint work with Mark Ban and Livni about an equivalence between online prediction and private classification. So the talk will consist of three parts. I will begin with giving some background and stating the main result. Roy will describe the proof idea, and Mark will finish with applications and suggestions for future research. So let us begin with understanding the first side of this equivalence. What is online prediction? So we consider the setting of prediction with expert advice. Here we assume a fixed class age of experts. Each expert is a Boolean function. And the goal is to design an algorithm that is given in a sequential manner, a sequence of examples, xi, yi, and that each round it first observes the unlabeled example, then it guesses the label, and then it observes the true label. And the goal is to compete with the best expert in class. Namely, we want that the total number of mistakes made by the algorithm will not exceed by much the total number of mistakes made by the best expert in class. And we call this difference the regret of the algorithm. The main definition in this context of learnability is that the class H as a class is only learnable if there is an algorithm that learns it with sublinear regret in the number of examples. So the per example regret vanishes when the number of examples is large. Okay, so this is about the first part. Now let us understand the second part. What is private classification? We begin with classification. So we consider the PAC setting by variant, the probability approximately correct setting by variant. So here again, we have a comparator class H of hypothesis. Again, these are just Boolean functions. And now the algorithm is given an IID sample of examples, which is drawn from some unknown distribution D. And it outputs an hypothesis H. And the goal, like before, is to compete with the best hypothesis H star in the class. So the probability that our output hypothesis makes a mistake on a new example is at most this probability with respect to the best H star in H. So this is called the population loss. Okay, and class H is PAC learnable if it can be learned by an algorithm whose excess loss vanishes when the number of examples goes to infinity in a rate which is independent of the input distribution D. Great. Now we will discuss the final part of this equivalence. What does it mean to classify privately? So the standard definition in this context is of differential privacy. And the goal is to, as we say, to perform statistical algorithms while protecting the privacy of individuals. So you can imagine a scenario where we want to use real medical data to train some deep neural doctor. But individuals may be afraid to contribute their data because they don't want their personal data to be leaked. So differential privacy guarantees that the participation will not affect the probability of any bad event that the individual may be afraid of. So let us now consider give the formal definition. And so we will need the following notation. So we said that two numbers, x and y, are equal up to epsilon delta if up to multiplying by e to the epsilon, and e to the epsilon is roughly 1 plus epsilon, and adding delta, then x and y are the same. Right? So up to applying an affine transformation, which is very close to the identity, x and y are the same. Now we say the two distributions P and Q are indistinguishable, epsilon delta indistinguishable, if for every event E, the measures P and E and Q and of E are epsilon delta equal to each other. Now for epsilon delta. Okay, now we will define what is a differentially private algorithm. So consider a randomized algorithm, right? So the algorithm has to be randomized for this definition to make sense. So our randomized algorithm in learning gets a sample, which is just a sequence of examples. And since it's randomized, then the output A of S is a random hypothesis. So it's a distribution of a hypothesis which depends on the internal randomness of the algorithm. So we say that the algorithm is epsilon delta differentially private for every pair of neighboring inputs. So if you change only one entry in the input, this means to be neighbors, then the induced distributions of the outputs are indistinguishable. Okay, so if you change one example, the participation of each single example will not affect the output distribution by much. So this is a strong form of stability. It's a robustness of the output under small changes to the input. So now we are ready to give the definition of DP pack learnable. So a class H is differentially private pack learnable if it can be learned in the pack model by an algorithm which is epsilon delta differentially private. And the epsilon delta parameters are set in this definition so that epsilon is a constant. So let's say epsilon is 0.1, and delta has to be negligible in the input sample size. So morally, DP learning is just pack learning by a DP algorithm. And DP algorithm is just a very, very stable algorithm. Okay, now we can discuss the main result. So indeed, as the title suggests, our main result says that the properties of being differentially private pack learnable and being online learnable are equal, or equivalent. And let me know that the DP learning implies online learning was proved in a joint work with Alon, Livni, and Maliaris 2 years ago. And in this work, we proved the second direction that online learning implies DP learning. Let me also know that this equivalence also gives some quantitative information about how the rate changes, but the constants concealed by this big O notation are very bad. So there is a tower-like deterioration in constants in this direction and exponential deterioration in this direction. So in a sense, the equivalence is information theoretical. It may also be interesting to know that it is based on a combinatorial perspective of learnability and on a new notion of algorithmic stability, which Roy will discuss next in more detail. But let me, so the last thing I want to say is that despite these caveats, still this equivalence gives a formal manifestation of connections between differential privacy, computation in adaptive environments like online learning, and stability. And so it gives a very abstract and formal equivalence, which somehow is, demonstrate these useful connections. Okay, so now I will let Roy tell you more about the proof overview. Thank you.
Thank you very much. I will not go over the proof idea behind our result that online learnability implies DP learning. As Shay stated, previous results showed that DP learning implies online learning, hence we obtained the equivalence. Now, I also want to mention that I will focus here on the realizable case, where the general case then follows on a generic reduction due to Alon, Baiman, Moran, and Stemmer, and I will not cover this part. The first step in the proof, we introduce a new notion called global stability. I will give a high-level definition in a minute. Then we prove the following two results. First, that the global stability implies private learning, and then that online learning implies global stability. Clearly taken together, the result will follow. Now, so first, what is global stability? At a high level, without going into any rigorous definition, an algorithm is globally stable if there exists an output age such that with some constant probability, we observe age as the output of the algorithm. So the probability is taken over both sample and the random bits of the algorithm. So H may depend on the distribution of F. So now as planned, first we show that global stability implies private learning. Showing that global stability implies private learning follows from standard existing result in differential privacy. We basically exploit a private algorithm that, given a list of elements, publishes the frequency of each element in the list with some error. With such a mechanism and a globally stable algorithm, our private algorithm works as follows. We run the learner multiple times, and then we give it a list of hypotheses. And then we publish the frequency of every hypothesis privately. And because one hypothesis has large frequency, we know that the output will include one hypothesis with high frequency. And because the algorithm is learning, we also know that any hypothesis with low frequency has to be good, because a learning algorithm doesn't output bad hypotheses too much. So now you can take this private list and you can output any hypothesis in it with large frequency, and you know that it's going to be good. So the main challenge remains to show that online learnability implies global stability. And that means that from now on, I won't care about privacy anymore. The procedure I will present are going to be highly non-private, but that's okay because they're going to be globally stable. And then using the previous result, I can just privatize it. So to give an exposition of the result, I want to go back to online learning, and I want to consider a special case that can be thought of as a realizable setting. It is also known as a mistake-bound model and was introduced by Littlestone in '87. The setting is very similar. We continue to consider an online game between learner and adversary, but now the adversary is constrained to choose a labeling that must be consistent with one of the hypotheses in the class. And the learner is required to achieve constant regret, which means that the number of mistakes he makes must be bounded. And in terms of online learning, it turns out that the mistake bound of a class also characterizes the rate of regret. So this is a result by Ben David, Pal, and Shalem Schwartz that showed that the optimal rate of regret is given by square root dt log t, where d is a mistake bound of the class we are learning. So every learner bound class has finite mistake bound, which, by the way, is also the Littlestone dimension of the class. So, so next we set out to prove that online learnability implies global stability, and we're going to use a mistake bound. What I want to do here is to prove the case where the Littlestone dimension is 1 or 2, namely mistake bound is 1 or 2, and I want to show that it implies global stability. These two cases contain the main ingredients of the proof. So for Littlestone dimension 1, I'm going to consider an algorithm that runs over the whole sample as a sequence online and then outputs the predictor of the next point. What I claim that this algorithm is maybe we'll need to alter it a little bit, but basically it is already globally stable. And to see that, we're going to consider two cases that depend on the distribution of the data. The first case is that it is unlikely that the algorithm makes mistakes. So you give it a sample and it runs over it and doesn't make any mistakes. The second case is that it is likely that the algorithm will make a single mistake along the sequence. Obviously, likely and unlikely should be quantified, but I'm giving here a proof overview. So we're not going to do that. So for the first case, we can simply take the prediction made by the online learner on the first sample because it is unlikely that it's going to make a mistake, as that's basically the assumption. So obviously it's not going to make a mistake on the first sample. So this hypothesis is already good, and it is independent of the sample. It doesn't depend on the sample anymore, hence it's going to be globally stable. In the second case, what we can show is that every time it makes a single mistake, it needs to provide the same hypothesis. So if this happens frequently, then again, the algorithm is stable. So to see this, suppose that S is consistent with H star. S is a sample. It is consistent with H star. And suppose we ran the algorithm, made one mistake, and now we have an hypothesis that is different than H star. That means that there is an X that they disagree on. And then basically I can generate a new sequence where the algorithm makes a second mistake, which is unlikely, which is impossible because the mistake bound is 1. So if I made one mistake, I had to choose H star. So every time I make one mistake, it's the same hypothesis. So the algorithm is globally stable. Now let's consider the case where we have a mistake bound 2. So we first have two cases that are very similar. The algorithm either always makes only 0 mistake, or that it is likely that the algorithm will make 2 mistakes. These two cases are treated exactly the same way as before. Only the only issue is that now they are not inclusive. We have a third case where the algorithm might make a single mistake, almost always. And then we also have two cases. First, let's assume that by chance the algorithm is globally stable, then okay, then we are done. And if we are not that lucky, then what we need to do is the following procedure. We sample 2 samples, and now consider the output hypotheses, which are different because it's not globally stable. And we find an X that they disagree on. We're going to guess the label of X, and we are going to guess it with probability half correctly. And let's assume H1 is wrong, then we're going to run the algorithm on the sample S1 and then X with the label that we guess. So we're going to make 2 mistakes on this sample. And what we basically done is we constructed a sampler that generates new sample that with positive probability are consistent with the original hypothesis. And also the algorithm makes two mistakes on them. So as before, it has to be stable. And now you can guess what happens if you have a mistake bound 3 and 4. You just either the algorithm is stabilized or you just keep on finding points that he will be wrong on, and then you make another mistake until you reach the mistake bound. So this is.
Thanks, Roy. In the last part of this talk, I'll discuss a few applications of our main result, describe some more of the context and recent related work, and wrap up with some of our favorite open questions. To remind you, our main contribution is a proof that every class of functions that is online learnable is also privately pack learnable. Equivalently, if a class has finite Littlestone dimension, then it has a private pack learner. The main algorithmic consequence of this result is, of course, a generic recipe for constructing differentially private learners. To be able to serve up this recipe, it's a good idea to understand what classes are online learnable. First, every finite class has finite Littlestone dimension. It was already known that all finite classes are privately learnable. So our recipe is most interesting for infinite classes that nonetheless have finite Littlestone dimension. One simple example of such a class is that of point functions, indicators for a single point over a possibly infinite data domain. It was already known that any such class was privately learnable with a number of samples independent of the domain. But another example, which we believe is new to our work, is any class consisting of the indicators for the d-dimensional affine subspace of a finite dimensional vector space. Any such class has Littlestone dimension d, even when the underlying field is infinite. This example can in turn be generalized to the class of solutions to systems of low-degree polynomial equations. And if you're up for some more intense examples from algebra and differential geometry, you can take a look at Chase and Freitag's survey for examples from model theory, where the Littlestone dimension is a central tool for studying so-called stable theories in that area. Our results have other algorithmic applications in the theory of private learning as well. One is to understanding how the differential privacy parameters epsilon and delta affect private learnability. Tight results are known for showing that one can generically improve the epsilon parameter of private algorithms. Namely, if you start with a private algorithm with a large value of epsilon, then pre-processing it by randomly subsampling a p fraction of the input data set improves its privacy guarantees to roughly p times epsilon. Subsampling gives a similar improvement to the delta parameter as well, but it's not able to amplify, say, a weak value of delta that is inverse polynomial in the sample size to a strong value that is inverse exponential. Our result shows that such an amplification is always possible, at least in principle. If a class is privately learnable with a weak value of delta, then it has finite Littlestone dimension. And hence our result shows that it's privately learnable using a negligible value of delta as well. Now it's a bit tortuous that this basic fact has to go through the characterization connection to online learning. And indeed, this proof does not give an explicit learner with improved privacy guarantees. An interesting open question is to determine whether there's transformation that can be made constructive and algorithmic. I'll move on now to discussing some more recent related work on the connection between private and online learning. First, I'd like to highlight a recent paper of Jung Kim and Tawari, who extended this equivalence to more general learning problems. This addressed a problem that we asked in a previous version of preprint of our paper. For multi-class classification, where each example can be labeled according to one out of k labels, they used the generalization of the Littlestone dimension to show that online learnability is equivalent to private learnability. For regression problems, where labels can be arbitrary real numbers in, say, the interval 0, 1, they proved that the direction that private learnability implies online learnability. For regression, the converse remains an open question. Further work has addressed the question of whether computationally efficient transformations exist between online learners and private learners. The equivalence we've discussed so far is information theoretic, but neither direction of the equivalence maps polynomial time algorithms in one setting to polynomial time algorithms in the other. Some progress has been made on understanding whether efficient transformations exist. For instance, Gonen, Hazan, and Moran showed that a subclass of efficient, pure, differentially private learners can be generically compiled into efficient online learners. Unfortunately, under cryptographic assumptions, it turns out that such a compilation cannot exist for efficient private learners in general. The converse question of whether efficient online learners can be turned into efficient private learners is again a nice open problem. Our transformation from an online learner into a globally stable learner, and hence into a private pack learner, requires invoking the online learner exponentially many times in the Littlestone dimension, which makes it far from efficient. Finally, I'll wrap up the talk with a few more open problems that our results raise. Our equivalence between online learning and private learning exhibits tight asymptotic dependencies on regret and generalization error. However, the big O's here hide quantitative gaps that are significant at finite sample sizes in the private pack setting and at finite time horizons in the online setting. For instance, the conversion from private learners to online learners hides a loss in parameters that's a tower of exponentials. Yet this loss turns out to be inherent, even for the simple class of one-dimensional threshold functions. Our work's conversion from online learners to private learners, meanwhile, incurs an exponential loss in the Littlestone dimension. But as far as we know, this loss could be eliminated entirely. Thus, it's natural to ask whether our algorithm's dependence on the Littlestone dimension can be improved from exponential to linear. More ambitiously, it would be ideal to find another combinatorial parameter that characterizes the excess error of private pack learners up to a constant factor, even at finite sample sizes. Our current transformations from online learning to private learning is improper. The hypothesis produced by our learner is not necessarily itself a function in the class H. Does online learnability imply private pack learnability, even for proper learners? An affirmative answer would have interesting consequences for private algorithm design. It turns out that a proper private pack learner for a class H can be used to privately approximate the expected value of every function in H on a sensitive data set. This is equivalent to privately generating synthetic data, which is as useful as the original data, at least as far as the functions in H are concerned. Finally, our result was driven by the intermediate notion of global stability. It would be interesting to develop a deeper understanding of its properties, especially as they relate to generalization. Note that global stability seems closely related to the notion of pseudo-deterministic algorithms, as first studied by Gatt and Goldwasser. It would be interesting if such a connection could give a principled way of designing new globally stable learning algorithms. With that, thank you for listening to our talk, and we look forward to your questions and comments at the conference.